Good morning. My name is Kavitha M. I am working as an assistant professor in the Department of Civil Engineering of Rajagiri School of Engineering and Technology. Today, I'll be continuing from my previous lecture where I had spoken about specific energy and specific energy curve in the fluid mechanics course for civil engineering students of second year. Today, we'll be looking into the topic of hydraulic jump. So, first, let me introduce to you the concept of hydraulic jump. Hydraulic jump is the rise of water level which takes place due to the transformation of stable shooting flow or supercritical flow to stable streaming flow or subcritical flow. So, from unstable supercritical flow, the flow is transforming into stable subcritical flow. So the definition of supercritical and subcritical flow has already been discussed in the previous lecture. So here we'll be looking into how the transformation of supercritical flow to subcritical flow takes place, and the process in which this rise of water level takes place is known as the hydraulic jump. So here you can see initially it is supercritical flow. Supercritical flow is characterized by low depth and very high velocity, and here it is getting transformed into subcritical flow. Subcritical flow is characterized by high flow depth and low velocity. So the transformation from supercritical flow to subcritical flow. So in between the flows, supercritical and subcritical flow, you can see a turbulence taking place in the form of a jump. That is the turbulence that is taking place over there when supercritical flow transforms into subcritical flow. That particular jump is known as the hydraulic jump. So we will be discussing in today's lecture, we will be discussing about hydraulic jump. So here we have a video. This was a YouTube video uploaded by Armfield Education. You will be able to view it if you go to the YouTube. Also, I have slightly shortened the video. Here they are demonstrating the hydraulic jump in a laboratory flue. Okay, so we'll just look at how a hydraulic jump is taking place. You can see that the water is flowing. You can actually see the hydraulic jump taking place here. There. You can see the jump, the transformation taking place. That is the jump taking place from the upstream depth to the downstream depth. This is the subcritical flow portion. That is the jump taking place. You can see the difference in water levels at the upstream and downstream sections of the flue. The downstream section is characterized by high flow depth and very low velocity. The upstream flow depth, we'll be focusing on the upstream flow depth. Upstream flow depth is supercritical flow. Supercritical flow is characterized by very low flow depth. You can see here, very low flow depth but very high velocity. It's known as shooting flow. So upstream flow depth is characterized by very high velocity and low depth, and the downstream flow is characterized by high depth and low velocity. And you can see the hydraulic jump forming in the video. So this is just to demonstrate what a hydraulic jump looks like. So now we are going to derive a mathematical expression for hydraulic jump. We're going to analyze the hydraulic jump. So before analyzing the hydraulic jump, there are a few assumptions that we should keep in mind. One of them is that the loss of head or loss of energy due to friction is negligible. That is, in the free body diagram that we're going to draw, we will not be considering head loss due to friction. We are considering the flow to be uniform and the pressure distribution to be hydrostatic before the jump and after the jump. That is, the flow depth, the supercritical flow before the jump is uniform and pressure distribution is hydrostatic, and the subcritical flow after the jump also, the flow is uniform and pressure distribution is hydrostatic. The next assumption is that the channel is horizontal. So when we were deriving Chassis equation earlier in module 3, we had taken the channel to have a mild slope, which meant that there was a component of weight acting along the flow. However, when we are analyzing the hydraulic jump, we consider the channel to be horizontal, which means that the weight component in the flow direction is negligible. Next is the flow is steady, that is, flow does not vary with time. Now, momentum correction factor is taken to be unity. Now, I'll explain why we have taken momentum correction factor to be unity. So, while we are analyzing the hydraulic jump, we cannot use energy conservation equation. Energy conservation equation can be of many types. You can use Bernoulli equation, where you have considered all the forces, all the energies, pressure energy and the weight, etc. However, energy conservation equation cannot be used to analyze a hydraulic jump, basically because energy is not conserved in a hydraulic jump. There is a loss of energy taking place due to the turbulence happening in the hydraulic jump. And so we will not be using energy conservation equation to analyze the hydraulic jump. Instead, we will be using Newton's second law. Newton's second law, everybody knows, force is directly proportional to the rate of change of momentum. And that is what we are going to use to analyze the hydraulic jump. Now you would understand, when we were talking about the assumptions, we had considered the momentum correction factor to be unity. This is because we're going to consider the momentum equation, and we are not going to consider momentum correction factor anywhere. We are going to consider momentum correction factor as unity, and we are going to apply Newton's second law to analyze hydraulic jump. Now, this is a very lengthy analysis. It's going to take a lot of space and it's going to take a lot of time. So what you are going to do, what you can do is, you can take a piece of paper and write along with me as I am explaining the derivation. You have to derive it along with me so that you understand the derivation. It will be difficult for you to understand by just looking and watching the derivation. It will be difficult for you to understand the derivation like that. So it will be better if you could actually take a paper or take your fluid mechanics notebook and derive the equation along with me. So this is your hydraulic jump. I'm going to take a small laser pointer. So this is the hydraulic jump. This is the flow depth Y1 and this is the flow depth Y2. Y1 is the upstream flow depth where the flow is supercritical, and Y2 is the downstream flow depth where the flow is subcritical. You can see that flow is uniform before the jump and after the jump. That was one of our assumptions. Another one of our assumptions was that the channel flow is horizontal. It is horizontal, as you can see. This is the pressure distribution upstream and this is the pressure distribution downstream. This is the net pressure force acting upstream and this is the net pressure force acting downstream of the flow. The velocity of flow upstream will be taken as V1 and the velocity of flow downstream will be taken as V2. Now, applying Newton's second law, F1 minus F2 is equal to mv2 minus mv1 by time. That is rate of change of momentum. Rate of change of momentum is change in momentum divided by time. So the net force F1 minus F2 is taken as mv2 minus mv1 by time. So from our previous modules, we know that mass by time is density into discharge, rho into Q. So I'm substituting m by t as rho into Q. So F1 minus F2 becomes rho into Q into V2 minus V1, where V2 and V1 are the velocity downstream and upstream of the hydraulic jump. Now, hydrostatic pressure distribution means that F1, which is the pressure force upstream, is rho g A1 Y1 bar, and F2, which is the pressure force downstream, is rho g A2 Y2 bar. So I'm going to substitute for F1 and F2. I will get rho g A1 Y1 bar minus rho g A2 Y2 bar is equal to rho into Q into V2 minus V1. I see that rho is constant throughout. I will cancel rho and end up getting g A1 Y1 bar minus g A2 Y2 bar is equal to Q into V2 minus V1. Now I'm going to rearrange this slightly. All the expressions with subscript 1, I'm going to keep it on one side and all the expressions with subscript 2 I'm going to take, or I'm going to keep on the other side. So I will get QV1 plus GA1Y1 bar is equal to QV2 plus GA2Y2 bar. Now V1 I know is discharge divided by area 1, and V2 is discharge divided by area 2. So I'm going to substitute that in this expression. I'll get Q squared by A1 plus GA1Y1 bar is equal to Q squared by A2 plus GA2Y2 bar is equal to. So I will get, now I'm going to divide throughout by G. I'll get Q squared by A1G plus A1Y1 bar is equal to Q squared by A2G plus A2Y2 bar. Now you can notice something here. It's being emboldened. It's actually kept in bold. Now you can notice the expression on the left hand side and the right hand side of this equation. And you can see that except for the subscripts, the terms are the same. Q squared by AG plus AY bar. So instead of writing it as Q squared by A1G plus A1Y1 bar is equal to Q squared by A2G plus A2Y2 bar, I can simply write Q squared by AG plus AY bar as a constant. And that's what I'm going to do. So I'm going to write Q squared by AG plus AY bar is a constant. Now this quantity Q squared by AG plus AY bar is what is known as specific force. This quantity Q squared by AG plus AY bar is known as specific force. So upstream and downstream of a hydraulic jump, the specific force is going to be a constant. Now, this is something that I have to explain. Now, I have here the specific energy curve and I have here the specific force curve. The specific force curve is a curve between specific force and depth of flow. And the specific energy is the curve between specific energy and depth of flow. And what you can see is that this is Y1 and this is Y2, the depth of flow upstream and downstream of the hydraulic jump. If I plot Y2 on the specific force curve, or if I correspond to Y2 on the specific force curve and Y1 on the specific force curve, you can see that it corresponds to the same value of specific force. Like we discussed before, the specific force is constant upstream and downstream of the jump. And so, corresponding to one value of specific force, I can have two depths, Y1 and Y2 for a hydraulic jump. Interestingly, Y1 and Y2 on the specific energy curve, you can see, does not correspond to the same value of energy. Here you can see that Y1 corresponds to greater energy E1 and Y2 corresponds to the lesser energy E2. And there is an energy difference delta E between these two values. This is because the energy with which flow is happening upstream with depth Y1, that energy gets dissipated, or that energy gets lost during the turbulence of the hydraulic jump, and then it reaches the downstream depth Y2. So the energy of flow at downstream with flow depth Y2 would be lesser than the energy at the upstream with flow depth Y1. So Y1 and Y2 do not correspond to the same value of specific energy. Y1 and Y2 of a hydraulic jump do not correspond to the same value of specific energy. However, they do correspond to the same value of specific force. That is why these three graphs or these three figures have been taken together in order to compare them. So from this graph, it is clear that Y1 and Y2 are not alternate depths. They are something else. Alternate depths are those depths that correspond to the same value of specific energy. So the depths Y1 and Y2 of a hydraulic jump are not alternate depths. So they have to be given another name. So Y1 and Y2 are the upstream and downstream depths of a hydraulic jump. They correspond to the same value of specific force. They are known as conjugate depths. Y1 and Y2 of a hydraulic jump are called conjugate depths. They correspond to the same value of specific force. So depths that correspond to the same value of specific force are known as conjugate depths. The depths corresponding to the upstream and downstream conditions of a hydraulic jump are also called conjugate depths because they correspond to the same value of specific force. They can also be called initial depth and sequent depth. Y1 is initial depth and Y2 would be the sequent depth. Now we're going to continue with our analysis. Analyzing further, we found out that the specific force upstream and downstream of the hydraulic jump was the same. So I've written Q squared by A1G plus A1Y1 bar is equal to Q squared by A2G plus A2Y2 bar. Now we know that A1 is width into depth, so B into Y1, and A2 is B into Y2. We also know that Y1 bar is Y1 by 2 and Y2 bar, which is the centroid of Y2, is Y2 by 2. So I'm going to substitute these two terms, and I'm considering a rectangular channel here. So considering these assumptions, considering these new formulae, I'm going to substitute it back, and I'm going to get Q squared by by1g plus by1 squared by 2 is equal to Q squared by by2g plus by2 squared by 2. So now I'm going to take the width B. I'm going to divide throughout by width B. I'm going to get Q squared by B squared y1g plus y1 squared by 2 is equal to Q squared by B squared by 2g plus y2 squared by 2. We all know that capital Q by capital B is small q, discharge per unit width. So Q squared by B squared becomes small q squared. So I'll get small q squared by y1g is plus y1 squared by 2 is equal to small q squared by y2g plus y2 squared by 2. So I'm going to rearrange this. The q squared, small q squared terms, I brought it together. So Q squared by y1g minus Q squared by y2g becomes equal to y2 squared minus y1 squared by 2. So I've taken it outside. Q squared by g into 1 by y1 minus 1 by y2 is equal to y2 squared minus y1 squared by 2. Now taking the LCM, Q squared by g into y2 minus y1 by y1 y2 is equal to y2 minus y1 into y2 plus y1 divided by 2. y2 minus y1 on both sides will get cancelled off. I will end up getting Q squared by g is equal to y1 y2 into y2 plus y1 divided by 2. Again, you can see that this particular expression is written in bold. However, this is not the final expression. Yet, I am going to put a box around this equation. That is because this is not the final expression. However, this equation is very useful when you're doing numerical problems. And so, you can keep it aside as a useful formula, but we're going to analyze further than this. We're going to analyze further than this, but this is a very useful formula, so you can keep it in your mind. So you've got Q squared by g is equal to y1 by 2 into y2 plus y1 by 2. Now we're going to go further than this. 2q squared by g is equal to y1 y squared by y1 y2 squared plus y1 squared into y2. I open the brackets. Here, it's an interesting equation here because this is a quadratic equation. This can be considered to be a quadratic in y1 or a quadratic in y2. If I'm considering it as a quadratic in y1, I can write this above equation as y2 into y1 squared plus y2 squared into y1 minus 2q squared by g equal to 0. You can see here quadratic in y1 means y1 is the unknown and all the other remaining terms are the coefficients. So I can write it in the form ax squared plus bx plus c. That is what I've written. If I want to write it as a quadratic in y2, I can rearrange this as y1 y2 squared plus y1 squared by 2 minus 2q squared by g equal to 0. So I can either consider it as a quadratic in y1 or consider it as a quadratic in y2. So here I'm going to go further or analyze further by considering this equation to be a quadratic equation in y1. That is, y1 is going to be the variable and the remaining are going to be the coefficients. So you know how to solve a quadratic equation. A quadratic equation is solved by minus b plus or minus root of b squared minus 4ac divided by 2a. So the same equation I'm going to apply here to find out the solution for this quadratic equation. So the solution or the root of the equation will be y1 because it's the variable. y1 is equal to minus b plus or minus root of b squared minus 4ac by 2a. B is the coefficient of y1, which is y2 squared, and A is the coefficient of y1 squared, which is y2, and C is the constant term that is standing on its own, which is minus 2q squared by g. And so I'm going to substitute everything over here, and I'm going to get the expression as y1 is equal to minus y2 squared plus or minus root of y2 raised to 4 minus 4 into y2 into minus 2q squared by g divided by 2y2. So now I have simplified the expression, and I've got y1 is equal to minus y2 squared plus or minus y2 raised to 4 plus 8q squared y2 by g divided by 2y2. Now I'm going to divide the numerator and denominator of the right hand side with y2. So I will get y1 is equal to minus y2 plus or minus, when I divide with y2 inside the root, it becomes y2 squared, division by y2 squared. So it becomes root of y2 squared plus 8q squared by g y2. So and divided by 2y2, and that 2y2 disappears from there because I have divided the denominator also with y2. You can do this on your own. Instead of hearing me explaining the division, it would be better if you work it out on your own, because then you will get the logic. So I took y1 by y2, that is I took y2 to the other side. I got y1 by y2 is equal to minus 1 plus or minus square root of 1 plus 8q squared by g y2 cube divided by 2. Now, this is also not the final expression. I am still going to analyze it further. So this was where we had ended. y1 by y2 is equal to minus 1 plus or minus root of 1 plus 8q squared by g y2 cube divided by 2. Now this term 8q squared by g y2 cube, I could simplify it further. So I'm going to separate it out and I'm going to simplify it. Q squared by g y2 cube is the same as capital Q squared by b squared. Small letter q is discharge per unit with capital Q by b. So small q squared, I'm going to write it as capital Q squared by b squared into g y2 cube. So I am going to split the denominator into b squared y2 squared into g y2, because q squared divided by b squared y2 squared is q divided by by2 the whole squared. Q divided by by2 is nothing but v2, or discharge divided by area is nothing but velocity. So q divided by by2 the whole squared becomes v2 squared divided by gy2, which becomes equal to v2 divided by root of gy2 the whole square. Now if you remember the equation for fruit number, you know that v by root gy is fruit number fr, v2 by root gy2 is fr2, that is fruit number downstream, fr2 the whole square. So the whole expression small q squared by gy2 cube has now become fr2 square. And so I can substitute y1 by y2 is equal to minus 1 plus or minus root of 1 plus 8 fr2 squared divided by 2. So I'm going to discard the negative sign, because negative sign will give me a negative answer, which will not be practically possible. So I'm discarding the negative sign. I will get y1 by y2 is equal to 1 by 2 times minus 1 plus root of 1 plus 8 fr2 squared. This is the final expression that we were looking for, that we have derived for so long for the hydraulic jump. This is known as the non-dimensional equation of the hydraulic jump. If you look on the right hand side or on the left hand side, you can see that both of them are dimensionless. y1 by y2, a dimensionless term. On the right hand side also, a fruit number is a dimensionless number. And so on the right hand side also there is no dimension, on the left hand side also there is no dimension. So this equation is known as the non-dimensional equation of hydraulic jump. So in our analysis for hydraulic jump, when we considered the quadratic equation in y1, we ended up getting y1 by y2 is equal to half into minus 1 plus root of 1 plus 8 fr2 squared. And similarly, if instead of considering it as a quadratic in y1, I had told you that we could also consider it as a quadratic equation in y2. If we consider it as a quadratic in y2, instead of getting y1 by y2, we will get y2 by y1 is equal to half into minus 1 plus 8 fr1 squared. So you can see here that if the denominator is having subscript 2, then the fruit number will also be having the subscript as 2. Whereas if you're having the denominator as y1, then the fruit number would be fr1. So depending on the equation data that you have in hand, you can use either this form of the non-dimensional equation, y1 by y2 form of the non-dimensional equation, or y2 by y1 form of the non-dimensional equation. Depending on whether you have fr2 with you or whether you have fr1 with you, you can choose between the two non-dimensional equations. Now you can also get the same question to prove. Sometimes in the university exam, they can ask you to prove that y2 by y1 is equal to half minus 1 plus root of 1 plus 8 fr1 squared. So you should know which form of the quadratic equation you should choose in order to end up getting this answer. So if they are asking you to prove the non-dimensional equation of hydraulic jump, you can either prove this equation, or you can either prove y2 by y1 is equal to this equation, or you can also prove y1 by y2 is equal to this equation. However, if they have specifically asked you to solve one of these forms, you should know which quadratic you should take. Whether you should take the quadratic equation in y1 or whether you should take the quadratic equation in y2. So what you can do is, since we have proved for this, you can take a piece of paper and try solving for y2 by y1 also by considering the quadratic equation in y2. The procedure is the same, only a few changes, you will end up getting the answer. So we're going to go to do some numerical problems. This is the question. The depth of flow of water at a certain section of a rectangular channel 4 meter wide is given to be 0.5 meter. The discharge through the channel is 16 meter cube per second. Determine whether a hydraulic jump occurs in the channel. If a hydraulic jump occurs, what will be the depth of flow downstream of the jump? So first we'll write down whatever is given to us. The width is given as 4 meter. The depth of flow upstream, that is, so I've written it as y1, is given as 0.5 meter, and the discharge is 16 meter cube per second. The question is, determine whether a hydraulic jump occurs in this channel. Now, how do you make sure that a hydraulic jump occurs in a channel? Or how do you know whether a hydraulic jump occurs in a channel? For that, I'm going to calculate the velocity of the upstream flow. V1 is Q divided by By1. I get 8 meter per second. The fruit number of the upstream flow is V1 by root Gy1. I'm going to get 3.612, which is a number greater than 1. So we all know that for supercritical flow, fruit number should be greater than 1. So by getting FR1 is equal to 3.612, we have proved that since FR1 is greater than 1, the flow is supercritical in the upstream. If flow is supercritical in the upstream, hydraulic jump will occur. So that is the prerequisite for a hydraulic jump to occur, that fruit number becomes greater than 1 at the upstream section. If the fruit number at the upstream section is greater than 1, we can prove that the non-dimensional equation. We know that y2 by y1. Here you can see that I know y1, I know the value of y1. I also know the value of fr1. So I'm going to use the non-dimensional equation y2 by y1 is equal to half into minus 1 plus root of 1 plus 8 fr1 squared. So I'm substituting with the known data. I will get y2 by 0.5 is 4.632. Which means that y2 is equal to 2.316 meter. So this is how you solve for the conjugate depth of a hydraulic jump. Now all these numerical problems, what I want you to do is, I want you to solve it on your own first before referring to how I've done the problem, because there are a lot of different ways. You can use different methods to solve this. This is one of the ways in which you can solve this problem. Now we're going to determine the expression for energy loss. We all know that energy gets lost or energy is dissipated in a hydraulic jump. We're going to find out a mathematical expression for energy loss in a hydraulic jump. So we all know that the energy of flow is reduced after the occurrence of a hydraulic jump due to the turbulence. So the turbulence is dissipating a lot of energy in the jump, and so energy of flow is reduced after the occurrence of a hydraulic jump. So the energy loss associated with a hydraulic jump is given by delta E is equal to E1, which is the energy upstream, minus E2, which is the energy downstream. We know that E1 is greater than E2 because E1 is before the turbulence is occurring and E2 is after the turbulence has occurred. So E1 is definitely greater than E2. E1 is the specific energy upstream of the jump and E2 is the specific energy downstream of the jump. So E1 minus E2 is the change in energy or the energy loss associated with a hydraulic jump. So we know the expression for E1 is Y1 plus Q squared by 2G Y1 squared, and expression for E2 is Y2 plus Q squared by 2G Y2 squared. So the difference between the two is delta E. So I'm going to rearrange it as Y1 minus Y2 plus Q squared by 2G Y1 squared minus Q squared by 2G Y2 squared. I'm going to get Y1 minus Y2 plus Q squared by 2G common. I've taken outside, into 1 by Y1 squared minus 1 by Y2 squared. Now I want you all to please work this out on your own along with me, because you need to know how, or you need to practice how this derivation is being done. It's a derivation. It can be asked for the university exam. So as I'm doing it, you can derive it alongside on a piece of paper or in your FM notebook. So delta E becomes Y1 minus Y2 into Q squared by 2G into Y2 squared minus Y1 squared divided by Y1 Y2 squared. Y1 squared by 2 squared. Now Q squared by G we know is Y1 Y2 into Y1 plus Y2 divided by 2. Now this expression I had put it in a box while I was deriving the non-dimensional equation. We had put it in a box and I told you that this equation is not the final expression, but it will be useful in lots of numerical problems. It can also be used in the derivation for energy loss in a hydraulic jump. So I'm substituting Q squared by 2G as Y1 Y2 into Y2 plus Y1 divided by 4 into Y2 squared minus Y1 squared. I've split it up as Y2 minus Y1 into Y2 plus Y1 divided by Y1 squared into Y2 squared. So now what I'm going to do is I'm going to simplify this. Delta E, I'm going to take Y2 minus Y1 common outside. So inside the brackets I will get minus 1 plus Y2 plus Y1 the whole square divided by 4 Y1 Y2 after cancelling out all the common terms. Now I will simplify the terms inside the bracket. I will get Y2 minus Y1 into minus 4 Y1 Y2 plus Y2 squared plus Y1 squared plus 2 Y1 Y2. So 2 Y1 Y2 minus 4 Y1 Y2 will become minus 2 Y1 Y2. Y2 squared plus Y1 squared minus 2 Y1 Y2 would become Y2 minus Y1 the whole square. So Y2 minus Y1 into Y2 minus Y1 the whole square divided by 4 Y1 Y2, which means delta E is Y2 minus Y1 the whole cube divided by 4 Y1 Y2, and this is the energy loss associated with the hydraulic jump. Now I've written the unit is meter. You can see if you look at the expression Y2 minus Y1 the whole cube, unit is meter cube divided by 4 Y1 Y2, unit is meter squared. So meter cube divided by meter squared. The unit of energy loss is meter. Energy loss unit is meter if the energy loss that I've expressed is energy loss per unit weight of water. So you have to remember that delta E that we have found out for delta E is energy loss per unit weight. It's also known as head loss, and the unit of delta E is meter. So we'll go on with the numerical problems. Second question. The depth of flow of water at a certain section of a rectangular channel 2 meter wide is 0.3 meter. The discharge through the channel is 1.5 meter cube per second. Determine whether a hydraulic jump occurs in the channel. Find the height of the hydraulic jump, length of the hydraulic jump, and energy loss per kilogram of water. So we have the expressions. We know the terms that is given to us: width, depth, and discharge. We'll find out the velocity upstream using the formula Q divided by By1, which is 1.5 divided by 2 into 0.3. I'll get a velocity of 2.5 meter per second upstream. The Froude number upstream is V1 by root GY1. We obtained it as 1.457. So using this Froude number, I can use the non-dimensional equation Y2 by Y1 is equal to half into minus 1 plus root of 1 plus 8 FR1 squared. Substituting the known values, Y2 by 0.3 is equal to 1.62. So I will end up getting Y2 is equal to 1.62 into 0.3, which is 0.486 meter. So I've got the conjugate depth or the depth downstream as 0.486 meter. Now the height of the jump is definitely y2 minus y1, which is 0.186 meter. The depth downstream minus the depth upstream will give me the height of the jump. They have also asked for the length of the jump. Now I've not defined any expression for length of the jump in the theory that I've discussed before. It's because a very short expression for length of the jump. Length of the jump is 6 times the height of the jump. So this I have not explained, or I have not explicitly given this information beforehand in the slides. This is for you to understand. Please keep it in mind. The length of the jump is 6 times the height of the jump, and so the length of the jump comes to 1.116 meter. Energy loss per kilogram, y2 minus y1 the whole cube divided by 4y1 y2. Substituting the known values, I will get the energy loss to be 0.011 meter. So it's a simple problem, direct substitution. This is the next question. A sluice gate discharges water into a horizontal channel with a velocity of 6 meter per second and depth of flow 0.4 meter. The width of the channel is 4 meter. Determine the power lost in the hydraulic jump. So here, this is the given values. B is equal to 8 meter, velocity upstream is 6 meter per second, and depth upstream is 0.4 meter. So I'm going to calculate the Froude number upstream. I'm going to get V1 by root GY1. Substituting, I will get the value of Froude number to be 3.03. So now I can find out the depth downstream by using the non-dimensional equation of hydraulic jump. Y2 by Y1 equal to half into minus 1 plus root of 1 plus 8 FR1 squared. I'll substitute the given values and I'll get Y2 divided by 0.4 is equal to 3.814, which means Y2 I will get it as 1.526 meter. This is the depth of flow downstream. 1.526 meters is the depth of flow downstream. The question is asking me determine the power lost in the hydraulic. So I'm going to first calculate the energy loss. Energy loss is given by y2 minus y1 the whole cube divided by 4y1 y2. I get it as 0.585 meter. Now to calculate the power loss, I know that power is equal to energy by time. That is mgh by time. Mass by time is rho into q. So power is equal to rho into q into gh. Power loss or delta P would be rho into Q into G into delta H, or rho into Q into G into head loss. Head loss is the same as energy loss, and so I'll find out delta P as 1000 into 8. Now discharges velocity into area, so 8 into 0.4 into 6 into 9.81 into the head loss that we found out 0.585 meter. I will end up getting the power loss to be 110,185.92 watts or 110.185 kilowatts. This is the power loss. So if they ask you the loss of power or the power loss associated with a hydraulic jump, this is the formula for it. Now we move on to how a hydraulic jump is classified. A hydraulic jump is classified based on the upstream Froude number. That is the supercritical flow Froude number is used to classify hydraulic jump. Here I've made a table. The upstream Froude number, when it is 1 to 1.7, the type of jump is known as an undular jump. That is, small undulations will be happening on the surface. That is how we know that it's a hydraulic jump. When the Froude number is varying from 1 to 1.7 on the upstream side, it's an undular jump. The energy dissipation associated with an undular jump is very low. It's less than 5%. That is, out of the total energy, less than 5% energy is dissipated using an undular jump. When the Froude number upstream increases from 1.7 to 2.5, it becomes a weak jump. That is, your smooth surface will rise with small rollers and the energy dissipation is from 5% to 15%. When the upstream Froude number ranges from 2.5 to 4.5, the type of jump is an oscillating jump, and irregular pulsations creating large waves occur on the surface of the water, and energy dissipation ranges from 15 to 45%. When now again the Froude number upstream is increasing, you can understand that as the upstream Froude number is increasing, the hydraulic jump becomes more and more powerful. When the upstream Froude number becomes 4.5 to 9, the type of jump formed is known as steady jump. Steady jump is a jump that is insensitive to the downstream conditions it will form irrespective of what is happening downstream, and the energy dissipation is steady. It is 45 to 70% of the energy is dissipated during the jump. And when the upstream fruit number is greater than 9, it is a strong jump. It's a very strong jump, it's a very rough jump, and energy dissipation is 70 to 85%. So greater the upstream fruit number, the more stronger the hydraulic jump formed. The classification of the hydraulic jump based on upstream fruit number. Now, just a few practical applications of a hydraulic jump. So one of the applications is to dissipate the excess energy of water flowing downstream. So when water comes with all its force, it is going to erode a lot of soil and it is going to damage a lot of structures downstream. So in order to reduce the power or the energy of the water, we use a hydraulic jump. So hydraulic jump is practically used to reduce the energy of water flowing downstream. Another use of hydraulic jump is to mix chemicals in the water for good purposes. That is for disinfecting water or for giving it a particular content of mineral or something like that. You can use a hydraulic jump for efficient mixing. The turbulence of the hydraulic jump can be used in the efficient mixing of chemicals in the water. Then you can aerate the streams. When you aerate the streams, it will lead to biodegradation of waste. So lots of streams are polluted by biodegradable waste, and so you can aerate the streams by using hydraulic jump. You can insert oxygen into the hydraulic jump, and efficiently it will get mixed with the water, and this will lead to aeration. And so aeration of streams can be done using a hydraulic jump. Now, hydraulic jump is associated with rising of water level. So when rising of water level takes place, you can use it to divert water into the irrigation fields for irrigation channels. So raising water level for irrigation purposes is also a practical application of the hydraulic jump. And another one is desalination of seawater. Hydraulic jump is also used for the purpose of desalination of seawater. So these are some questions that has been given for self-assessment. You can work them out. Another type of question that can come is to derive the non-dimensional equation and to derive the energy loss associated with the jump. Theory questions like classification of hydraulic jump and the practical applications of a hydraulic jump can also be asked. Lots of questions usually come for the university exam from this topic. So I hope that you have gone through this topic and you have understood the topic and that you're able to answer questions that come from this topic. So thank you for listening, and I hope that you have understood.